Good news, we have made it to vectors. You will like vectors. They're much easier to work with, I think, and to understand and to just wrap your mind around in the beginning. So what the heck is a vector? I posted a short little clip from Despicable Me where he talks about what a vector is, which is kind of like a layman definition, which is true enough for what we want to talk about it. And then I posted an article that was linked from one article and links to actually you can click on there and link to a third article about what these are really mathematically, and read a little bit. I guess he has a little bit of a argument going with the guy from Khan Academy about some of his descriptions. We're not worried so much about what is the best definition. We're going to just kind of start getting used to working with vectors, and we want to understand what does vector algebra look like? What can I do with them? What do all these lovely words mean on this slide? So what's a vector? If you watch the Despicable Me clip, he kind of talks about it as a ray with a direction and a magnitude. And I think that's probably the easiest way to think about it. It's kind of like a little line segment. You're going to start at one point, you're going to end at another point. And how fast you're getting there is the magnitude. And we used to call that slope. And magnitude is going to feel very much like slope. And of course, slope feels very much like tangent, which is very much like your Pythagorean theorem, right? All of those guys are related, that distance formula, Pythagorean theorem, and tangent. And you can kind of even see it on here if you were to finish this triangle. You can see that it's clearly going up 2 and running 3. And so we would be able to find out what the length of this is. And that's going to be my magnitude, so how far it goes. It will be a big deal though where you end and where you start. So unlike with slope where it didn't matter who was x1, y1 or x2, y2, it will with this one. If I want to add and subtract, we're working on a real number plane. So these guys are going to have all the real number properties, and that's really nice. They'll be associative, they'll be commutative. But the way that it actually looks on the graph is a little strange. So if I had V and I wanted to take away W, so here's V. You can see this kind of little line segment here that's heading up with that positive slope, and then I have this one heading down. This one's heading up faster than V. And if I want to look at V minus W, I would take the V and put it on my graph, and then where V ended, I would link on the W, but I want to subtract W. So W looked like this. I have to flip that switch. So that's like we had with the radius. And there, and then where my V started to where W ends. So this is P1 for V and P2 for W. That's going to make my new vector of V minus W. So if I had two V's, here would be one V, and here's another two V's. And then I want to link three W's, 1, 2, 3, and I have this black vector in here. Fortunately, we don't do it like this very often. What normally happens is we're going to have numbers that we can just use the properties that you see here, and these very fancy properties are ones that you really know. This one that looks like absolute value, this is magnitude. Magnitude's got to be greater than or equal to 0. The negative that we'll look at is going to be a direction. So if I'm going 50 miles an hour, that's great. Which direction am I going? That's going to come from this negative sign in here. So it's the speed, not the direction. If the magnitude is 0, then it's a 0 vector. And that was one of the big issues that the author of that article I gave you had with some of the things that Khan had wrote, because he left off a few symbols here and there, and I can certainly relate to that. If you have a scalar on the inside, you can send it in or pull it out, very much like you can with absolute value. If I have a vector that I'm creating, that I'm starting at P1, which is at a negative 1, 2, and I'm ending at 4, 6, I can find out where I'm going, what the dimensions are almost really of that vector. Well, the position vector, instead of just floating around out in the middle of nowhere at, let's say, negative 1, 2, and 4, 6, if I want to talk about how long this is and where it is, I'm going to pull it back to the pole. And in doing that, I'll be able to get a little bit more information. So a position vector is the same vector that you just kind of slip back to that P1 is at the pole. 4 minus a negative 1, 5, 6 minus a 2. And so my vector is 5, 4. You can put it in this component form, or you can put it in the vector forms with i's, j's, and k's that we'll see in a minute. Either way is fine. And it looks just like that. If you have a couple of them and you want to add and subtract, and they actually gave you the numbers, we'll think about ij and eventually k at the end of the section. That's kind of like x, y, z, but it's not exactly like an x, y, z, because we can have vectors that are 4, 5, 6 dimensions. So how are you going to graph that? But if I want to talk about v plus w and I have a 4i plus 2j, you may also see them with little hats like this. That way you know that you're dealing with a vector and not just a random type of a variable in an equation. You would just add the two spots together. And so I would add the I components together, and I would add my W components together, and when I get that out, that's V plus W. Same thing with subtraction. I would subtract the I coordinates, subtract the J coordinates. What you get out is V minus W. It's very much like adding and subtracting polynomials, right? It's just a defined variable. If I have a scalar, I can just send my scalar through. So if I want to say 2 times v, where v is 4, 2, then 2 times that is 8, 4. So easy to work with, right? So easy to work with. A unit vector. A unit vector is kind of like a special position vector. It's going to pull your vector that's floating around out here. It's going to anchor it at the origin, and it's going to chop it off at the unit circle. So it's still opening the same angle and heading up the same direction, but instead of being a magnitude of 10, 12, whatever, it's only going to have a little radius of 1. So how the heck do you do that? We'll need to find out how long it is originally, which is pretty easy. If I know this is 6i to 8j, I got x and y. I can go ahead and find my magnitude, which, go figure, is Pythagorean theorem, right? The guy in front of the I squared, number in front of the y, j squared. Square and add them together, take the square root. That's your magnitude. Take your magnitude and chop down your original vector by dividing. And so 3/5 I minus 4/5 j is opening up the same direction and heading the same direction, but the 6i minus 8j, well, I didn't really draw this in the right spot, would be there, where my 3/5 negative 4/5 would stop there. So it just kind of gets sawed off a little bit early. If I want to find the direction that it's opening, I can use that xy idea and find the angle. So we can go backwards from tangent, sine, cosine, however you want to find it is fine. Very similar to when we converted from Cartesian over to polar. We're not going to look at that too much. Instead, what we are going to look at is something called the dot product. And before I get to the dot product, I want to give you a little bit of a description. So I'm going to put this link up to better explain about what a dot product actually is. If you have two vectors and you link them together, and we want to find what we call the dot product. I really like this picture where it kind of takes my red vector, right, makes a right triangle, it takes my blue vector, takes a right triangle, and it kind of starts to think about all the ways that these guys can be matched up so that they're going the same direction. So x's with x's, the y with the x with his y, and the y with his y. And they look at all of these different combos, and these guys will outdo themselves because they're orthogonal or 90 degrees. And so we're just looking at this pull and this pull. There's a couple of different examples on here about what this looks like in the real world, but I think the one that really makes the most sense, I'm going to scroll down, is Mario Kart, because everybody's played Mario Kart. So you know you're driving, right? Yoshi's here on his little motorcycle, he's doing his thing, and he's following a vector basically. He's going a direction with a specific speed. He hits these booster pads. All right, so the booster pad boosts the speed, but you gotta it only goes that one direction. So it's not like you come in this way and then you get to go whatever way you're going. It's pushing out like following that blue vector. The output that you get when you're traveling a little bit to the left at 90 degrees and you jump on something that's going a little bit to the right at 60 miles an hour, that output of that new vector, that's your dot product, right? So how fast are you going to be shooting out now? The dot product is going to be just a number. So after you crunch this number, it's going to be just a number, right? The bigger the number, the faster, the more impact that you had. So I thought that was a pretty good example of what a dot product is. How do you calculate it? It's actually pretty simple. And we saw it a little bit already. You take the I components and you multiply them. And you take J components and you multiply them, and then you add them together. That's it. So V dot W, it looks like a multiplication sign, and we've got some multiplication going on in there, but it's a dot, would be 4 times the 3 plus a negative 2 times the 2, and so your dot is an 8. That's it. Conveniently, they're going to be commutative, so W dotted with V will give you the same thing. You can dot with yourself, so imagine that you're going at a certain speed in a certain direction, and then your booster pad just so happened to go the same speed in the same direction. So if you ever walked on those like flat conveyor belt things, like at the airport, so you're walking on it, and it's maybe going, I don't know how fast it goes, like maybe it goes 10 feet a second or something like that. That's probably too fast. But then when you walk on it, you feel like you're just flying, right? Because you're going in the same direction, and your speed kind of gets compounded by the speed that's moving you forward. Or like running up the escalator, right? You're going the same direction, and those speeds that together are going to get you up faster than had you done it individually. So you can dot the same vectors. 4 times 4, negative 2 times a negative 2, you get the 20. You can do that with the W. Something dotted with itself, if you take the square root, you get the vector. So, I mean the magnitude. So the magnitude is kind of like the square root of a dot product when you dot with yourself. I can use that to help me find some angles. Because if the impact of the angle is a 0, then that means I'm going nowhere, which we saw a little bit on our description here. Right? If this is pulling this way and this is pulling that way, I'm not moving. I'm just going to be stuck in the middle, like suspended in the center. And so I don't get to get pulled to the right. I don't get to pull up or to the left or and up or down. And so we call things that create that suspension from the 90-degree angle as orthogonal. And so if it's orthogonal, then the angle between them has got to be 90. And think about the cosine of a 90-degree angle. It's a 0, right? So we can use all of these ideas by wedging them together. If I want to find the angle that these two vectors make, so I link the initial point for W and the initial point for V together. And I want to know what's the space in between them. First, I'm going to need to find the dot product. So I find U dot V, 2 times 5, negative 4 times 12. I get a negative 2. Then I'm going to need to find the magnitude of U. How fast am I going? 4 plus 16, so radical 20. Let's find out what's going on with V. 25 plus 9, 34, so radical 34. So V is going a little bit faster, but it's going in a different direction, right? So here's the pull for V. Here's the pull from U, and then here's kind of like the leftover in between them of that power struggle. U dot V is going to be your numerator. And then the two magnitudes are going to get multiplied together. And what you have just found then is the cosine of the angle. So then all you have to do is say inverse cos. What angle has the theta of a negative 0.077? About 94 degrees. If U dot V is 0, then the whole thing is 0. And so then we know that it has to be 90 degrees and that they're orthogonal. If you get it that you want to find the cosine of the angle and it's equal to a 1, well, where is cosine of 1, or in this case, it could also be a negative 1, then it's flat, right? And so that would be 0 or pi, and then that's when they're parallel, and the angle between them would be 0 because they just it's like they fell on top of each other. We'll use this idea again in the next section when we want to find direction angles.